All right, let's talk more about zeros of polynomial functions for section 4. We're going to use the fundamental theorem of algebra to determine the number of zeros of a polynomial function. We're going to find rational zeros of a polynomial function, talk about conjugate pairs of complex zeros, and we'll also find zeros by factoring again. Okay, and we'll look at this briefly, but this isn't something I'm probably going to make you use. But there is a rule that will help us find the signs for upper and lower bounds of real zeros. Okay, so first of all, the fundamental theorem of algebra. In a complex number system, every nth degree polynomial has precisely n zeros. Okay, it's real simple. So if our function has degree n, where it's positive, then it's got at least one zero in the complex number system. Okay? And specifically, it's got n zeros. Okay, we can factor these linear factors, which we've been doing. Let's take a look at an example then. The first degree polynomial, x minus 2, has exactly one zero at x equals 2. Would you agree? Yeah, pretty simple, right? It's a line, it's got a slope of 1 and a y-intercept of negative 2. So we know that the 0 is at x equals 2. So it's first degree, and it has a 0 at x equals 2. Okay, so try another one then. The second degree polynomial function. Okay, we can factor this into x minus 9, or x minus 3. X minus 3. In which case this has two real zeros at x equals 3, so it has a multiplicity of 2. Okay? So it's a second degree, and it has two real zeros. Yes?
So why have...
Okay. Alright, so let's look at the third degree one then. You'd expect this one to have three zeros. I can factor out an x, in which case I have x squared plus 4. Okay, and it's got one zero that's 0. So x equals 0 is a 0. There is two more, but they're complex numbers. We can get them from setting this factor equal to 0. X squared plus 4 equals 0. Subtract 4 from both sides. And then square root both sides, and you get x equals plus or minus 2i. Square root of negative 1 is I, and the square root of 4 is 2. So here's the other two. So there are three zeros, as you'd expect from a third degree. It's the fundamental theorem of algebra says. And there's one real one, two complex.
So
Okay. If it's a fourth degree, you'd expect there to be 4 zeros. Okay, so let's give it a try. This would factor, you can do a difference of two squares. You can do x squared minus 1, x squared plus 1. If you FOIL this out, then you get this. So I can see that this is really a difference of two squares. Maybe it would help you to write it like this, x squared squared minus 1, maybe even 1 squared. You can see it's a difference of two squares then. Just like our a squared minus 4, or our x squared minus 4 turned into x minus 2, x plus 2. This is really no different. It's just this time it's x squared that's being squared. So that's what would go here instead of x. So we can factor this difference. There's another difference of two squares right here. X minus 1, x plus 1. And then this right here doesn't factor. This isn't what we're going to call an irreducible quadratic. But once again, we can set it equal to 0 and get two complex solutions from it. So we'll square root both sides and we get x equals plus or minus I. So my zeros are x equals plus or minus I, and then also I have two zeros that are real, x equals 1 and x equals negative 1. So there's 4 zeros, plus or minus 1, plus or minus I. Two of them are real, two of them are complex. Like you'd expect, there's 4 zeros. Okay. All right. So next is this rational zero test. Okay. This rational zero test is helpful. I don't know that you'll use this, but if I take away your calculator and I ask you to find zeros of a polynomial, then this would come in really handy. So on a no calculator portion of a quiz or a test, if I ask you to find zeros of a polynomial, you might use this. It looks really confusing. It's not really that hard though. It tells you that the rational zeros, or the places that the rational zeros could be, would be at the ratio of p over q. Now what p and q are is they're factors of, p is a factor of the last coefficient, and q is a factor of the first coefficient. So let's just look at an example. If we have this polynomial, the potential zeros are at factors of p over q. Now, p is factors of -6, which could be -1, plus or minus 1, plus or minus 2, plus or minus 3. Those are the factors of 6, and plus or minus 6. Okay, the factors of q then are plus or minus, well, 1. That's it. So if you make a fraction of these, then the potential zeros are at plus or minus 1, which is from here. Okay, positive 1 over negative 1 would be a negative 1, and you know, negative 1 over negative 1 would be positive 1. So plus or minus 1 would come from here. Plus or minus 2, plus or minus 3, plus or minus 6. So what this tells you then is that these are the places where you want to check for zeros. Okay, the real zeros will be in here. So you can try them, you can plug it in for x, plug in 1 for x and see if it gives you a 0, plug in positive or negative 2, see if you get a 0. You'd have to try all of these. I know this is a long one, but basically if you don't have a calculator and you can't graph this to find out where the real 0 is, you could use this, this theorem, which all we have to do is take factors of the last coefficient divided by factors of the first coefficient, and these give you all the possible zeros. So you do all these combinations.
Wait,
So let's try to figure out where these zeros are. I'm actually going to cheat and pull out the calculator, and I'm going to graph this, because the calculator will give us the rational zeros. So let me plug this function in real quick. Okay, now when I graph this, I get this, this polynomial here. And it's got a 0 at -1 and positive 2. So I know -1 and positive 2 are the two zeros that are going to work from these lists of numbers here. That saves me time. Obviously, if I give you one of this on a no calculator quiz, I'll give you more time. Or I'll make it easier, because right now I have 1, 2, 3, 4, 5, 6, 7, 8 values to try in here to find out which ones are zeros, which would take a while. But let's try. What you would do is just try them. You plug in positive 1, and you get 1 minus 1 plus 1 minus 3 minus 6, which gives you, these cancel, 1 minus 3 is -2, so this would be -8. So that's not a 0. So positive 1 doesn't work, not a 0. Gives you -8. Then you try the next one, -1, plug in -1, and you get positive 1 minus -1 plus positive 1 plus 3 minus 6, which gives you 0. So this one works. Okay? Now you move on to the next one. You try, so right now I know one of the factors of this is x plus 1. So I got one of the factors because I found one of the zeros without the calculator. Now I move on to 2 and try both these. When you try positive 2, it works. So you try positive 2 and instantly you know next factor is x minus 2. And now we could do division to find out the other two factors. So we could factor this thing completely without a calculator using this rational zeros theorem. It's actually pretty helpful if you don't have a calculator. Okay? And none of these work if you try them. They're not, the only two rational zeros are -1 and positive 2. Alright, so conjugates, this is another helpful thing to know, that when a complex number, like a plus bi is a 0, its conjugate is always going to be a 0 for a polynomial. Okay? So that's what this says. Complex zeros occur in pairs. Let the function be a polynomial function with real coefficients. If a plus bi is a 0, then a minus bi is also a 0. And these are called complex conjugates, where you change the sign on the I term. Okay, you guys are going to have to find fourth degree polynomial functions then using this information. So I'll tell you that 3 of the zeros are at -1, -1, and 3i. And I'll ask you to write a fourth degree polynomial. Well, instantly you know another 0 is at -3i because that's the conjugate of 3i. And so the zeros are at x plus 1. There's two of them, so there's a multiplicity of 2. And then we have x minus 3i and x plus 3i as two of the other factors. If these are both zeros and the other two factors are here. I would multiply this out and I'd get x plus 1 squared times, this would be x times x, which is x squared. The middle terms are going to cancel, so all I have is the last two, which is going to be negative 9i squared. I squared is a negative 1, so this turns into x squared plus 9. So my factored polynomial that has these four zeros is right here. All right, let's just do another example then. I'm going to give you functions like this. Here's another fourth degree. And I'm going to tell you that one of the zeros is 1 plus 3i. Okay? And I'm going to ask you to find all the zeros. All right, so I know another zero is 1 minus 3i. Okay, so that makes this as x minus 1 plus 3i is one of the factors. And another factor is x plus 1 plus 3i. Right, so I know that if these are the two zeros, then two of the factors are x minus these and x plus these, right? I'm sorry, x minus, this is the sign that would change. These are the two zeros right here. So x minus this zero and x minus this zero are two factors of this polynomial. Now, I could find the other two now by multiplying this out. If I multiply it out, I get x squared. Actually, let me FOIL or distribute the negative sign first. In which case, I get x minus 1 plus 3i. And then distribute the negative sign here, x minus 1 minus 3i. Now I'll FOIL. X times x gives me x squared. X times negative 1 is negative x. X times 3i is positive 3xi. And then I'll go to the second term and distribute that. So negative 1 times x is negative x. Negative 1 times negative 1 is positive 1. Negative 1 times 3i is negative 3i. Now I'll go last and distribute that. So that would be, I'll move to the second line. Negative 3xi, positive 3i, and negative 9i squared. Okay, now let me simplify. Positive 3xi and negative 3xi cancel. Negative 3i and positive 3i cancel. I squared turns into a negative 1, so this would be a positive 9. And so I end up with x squared minus x. 9 and 1 make 10. So this is my quadratic factor that comes from these two zeros. So basically the zeros of this quadratic are 1 plus 3i and 1 minus 3i if you use the quadratic formula, or if you work backwards here. Now I want to find out what the other two, there's two more zeros obviously, I don't know if they're real or imaginary, but they're in here. So what I can do is divide this polynomial into this one, and I'll get the other zeros. Yeah, this and this added together would be negative 2x, so I missed a 2 right here as well. But let's divide that now, let's do long division. X squared minus 2x plus 10. And we're going to divide that into this polynomial, x to the fourth minus 3x cubed plus 6x squared plus 2x minus 60. And that's going to give us what's left over. There are two factors, so let's do this. You guys can do long division by now, so I'll just pause it and show the work, and you can look through it later. You can pause and look through this work if you want, but you should know how to do long division at this point. And so my answer then for the complete factorization is x squared minus 2x plus 10 times this other factor, x squared plus negative x minus 6. I want to see if I can factor this more. So let's see, this could be factored into x minus 3x plus 2. So here's the complete factorization of the original polynomial that was given. This is an irreducible quadratic, and these are the other two factors. They didn't ask for this though. All they asked for were the zeros. So the other two zeros are 3 and negative 2. Okay, so the first two zeros were the imaginary ones. One's 1 plus 3i, 1 minus 3i, so it's 1 plus 3i, 1 minus 3i, and 3 and negative 2. Those are the four zeros. And then here's the complete factorization if you're ever asked that question on a quiz or a test.